Hello, 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 everybody, and welcome back. We are going to be finishing up the 2014 Gauss paper in this video. That's right, we're on question number 4. Now let's take a look-see. So question 4, we've got a light bulb and 2 written parts. At least I think it's 2 written. Yeah. And it looks, just on the surface of it, like we're going to be dealing with circles. So let's dive right in. So, for a circle of radius 2 and a circle of radius 5 are externally tangent to each other at point T, and are tangent to a horizontal line at points P and Q. They've already got right angles here. If you connect a radius up to a point of tangency, you get nice little right angles. So if we were to draw a tangent line in here, we get nice little right angles, and it would show that OTC is actually a full line. They go on to say that. So points O and C are the centers of the circles, and OTC is collinear. This is a nice little fact here. And both OP and CQ are perpendicular to PQ. I remember the days where they wouldn't tell you that, and you'd have to figure it out for yourself. By constructing a line segment passing through O and parallel to PQ, determine the distance between P and Q. Alright, wow, this is an interesting one. They're actually telling me how I should do this, although it's a light bulb question, so they really just care about the answer. If it were a written question, we have to make sure that we would construct the line through O parallel to PQ, but they're just trying to get you to do right angle and do a little bit of Pythagorean theorem work, I think. We know the radii of the circles. In fact, we can now just draw this picture on our own. I should probably draw my circles first. Alright, those are some reasonably decent circles. Now, we might call this, so we've got OTC, P and Q, we might call this R or D or something to that effect. But we're going to get a nice little rectangle in here because it's parallel to PQ, and so OR hits the same line, CQ, this radius, at the same angle, which is 90 degrees. Now, we have a radius of 2 here and a radius of 2 here, 5 here, and CQ is also 5. And so if I subtract off this 2, because rectangles are parallelograms, so opposite sides of the same length, we would be left with a 3 up here. So what we've really got, if I highlight it in blue, is a nice little right-angled triangle with 3 and 7 there. And OR, because it's a rectangle, since OPQR is a rectangle, OR is the same as PQ. So it's just going to be this other side here. What is that? Well, it'll be, we use the Pythagorean theorem, the square root of the hypotenuse squared minus the known side squared. So it'll be the square root of 49 minus 9, square root of 40. And I'd probably leave it like that, although if you wanted to, I guess you could write 2 root 10. If you wanted to be particularly fancy, but when marking, we don't really care about that. So root 40 is good. Alright, so that's A part. Get another sheet of paper ready for B. Now, B and C, we're going to actually have to write up our answers and be careful here. Make sure everything's justified. So we've got a circle of radius 4. I'm going to assume that's the small one, because the other circle is radius 9. They're both tangent to a horizontal line, so we can drop these right angles just like they had. So D and E is shown. A third circle can be placed between these two, so it's externally tangent to each circle. Something like that. It looks like they're doing tangent circles down here as well. So it's externally tangent to each circle and tangent to the horizontal line. If DE is 24, determine with justification the radius of this third circle. So if I had a radius of R here, we could get some other lines. Now the whole thing might not be one line. It could be, but we might get at least 2 lines, and maybe have to do 2 right-angled triangles or something to that effect. So let's see if we can draw a little picture here. I'll put in green my other circle. And all be tangents to there's D, there's E. So we might call the centers A, B, and C, just to keep sort of the lettering the same. Might call the tangent points S and T. And I'm pretty sure I'm going to need to drop this perpendicular down here. Call this F. And so we should probably say that, you know, that A, C, B be centers as shown. ST, the points of tangency. Points doesn't have two S's in it. Points of tangency. And F, the tangent point to the line. So we've got all this shown. Alright, let's drop some radii. So we know this is 4, so is this length here 4. We know this is 9, and this length here is 9. We know the total distance here is 24. And then in blue, we could have R here and R here, trying to make it a bit more slanted. So I'd probably make the comment ASC are collinear, as are CTB. And we might say something like let R equal third radius. Okay. So, what can we do? Where can we go from here? I don't know. This little radius R, I don't know what exactly... Is it bigger than 4? Is it bigger than 9? Not entirely sure. Suppose we could try and make some assumptions. Actually, it doesn't matter if we have... so by constructing right triangles, because either 4 is less than R, in which case we plop this down here, and then this distance is R minus 4, so that's the other side. Or we have this all backwards, and R is actually shorter, and we drop the perpendicular down, and this will be 4 minus R. We'll get the same square. 4 minus R and R minus 4, they're negatives of each other, so they'll have the same square. We can see that df is the square root of 4 plus R all squared minus 4 minus R all squared. And similarly, FE is the square root of 9 plus R all squared. This bigger hypotenuse. And then we could, it's probably, R is probably less than 9, but we can't guarantee that for sure. But we know that no matter which way you slice it, you're going to have 9 minus R or R minus 9, doesn't matter which one, because they both have the same square value. Okay, so 24 is DE, which is DF plus FE. Okay, 24 is the square root, I can expand this out, 16 plus 8R plus R squared minus 16 minus 8R plus R squared plus the square root of 81 plus 18R plus R squared. minus 81 minus 18r plus r squared. A lot of that will cancel out. 16s will go away, so will the r squareds. So will the 81s. And so we'll be left with 24 is the square root of 16r plus the square root of 36r. So I can pull out a factor of 16, but I'll have to square root it. So we'll get 4 root r plus 6 root r. So we'll have 10 root r. 24 is 10 root r. And so dividing by 10 on both sides, 2.4, or I guess we could say 12 over 5 is equal to root r. So if I square both sides, r is going to be 144 over 25, which is a little bit more than 5. Actually, it's only slightly less than 6, I guess we could say. Okay. Now, if you're upset that I just chose 9 minus r instead of actually checking which one's smaller, you could, I guess, break this up into 4 separate cases. But I think a quick line saying something like, well, as long as we draw a line parallel to FE or DF, as we did in the first question, through either C or B, whichever one's lower, we'll get one of the legs of our triangle to be 9 minus r or r minus 9, and it doesn't matter because the squares will be the same. As long as you write something like that, you'd be fine. Okay? In fact, they might not even have marks assigned to that, but I would guess that they want some sort of argument out of you. And you know, it's easier than doing 4 separate cases if you can spot something like that, especially because it didn't really matter in the long run. We got the same r no matter what. Alright, now we've got C part. 3 circles with radii r1 less than r2 less than r3 are placed so they're tangent to a horizontal line and they're externally tangent to each other. F, G, H, I, J, K are the points of tangency of the circle. So depending on which circle, because if you move the smaller circle in between, the bigger ones can actually get closer. So the points of tangency of the horizontal line, these might be different lengths. The lengths F, G, H, I, J, K are in no particular order, are 18, 20, and 22. I'm going to guess the one with the fat one out here is 22, and this one will be 18, and this will be 20, but I don't know. I'd have to double check the geometry. Anyway, so in no particular order, 18, 20, and 22. Determine with justification the values of R1, R2, and R3. Ooh, okay, so that's kind of interesting. Although, thanks to the last 2 parts, maybe we're masters of this sort of work. I'm going to guess we connect radii, drop perpendiculars, that sort of thing. But you'll have sort of duplicate copies of R2 in this first one here. So there'll be an R2 and an R2, and you'll only get one R1 and one R3 here. That sort of a thing. Okay. Oops, wrong button. I gotta be over here before I can... we'll get another page. Okay. So, if I imagine 3 circles set up as suggested. How do I want to do this? I'd like to get sort of a general formula here. That would be quite nice. So imagine 3 circles set up as suggested. We know R1, R2, R1 is the smallest one, R3 is the biggest one. We'll get to draw something like that, I guess. So, drop radii to tangent points on the line and to tangent points between circles, let's say. We'll call these tangent points S and T, I guess. I'll have my centers be A, B, and C here. So we'll also, I'm going to color code these. So red for the first one, blue for the next one, although these, I guess, should be collinear. So we'll redo that center in a moment. And this one should be blue. Alright. So ASB collinear, BTC collinear. If we draw lines parallel to the tangent line, we can create two right triangles. Now, I know which one is going to be the longer side if I know that, for example, we've got R3 here and R1 here. I'm guaranteed to say, well, it's going to have to cut across like this. Although, again, that really doesn't matter because all we've been dealing with so far are these squares. So what I'd like to say is, instead of, let's just call these radii A's, B's, and C's. And that way I don't have to worry about these individual cases of R1, R2, R3. Because we're going to have the exact same picture 3 times. I don't want to do the same work 3 times. So I'd rather do this sort of shortcut of saying, well, you know, draw the parallel lines. They'll cut the longer of the 2 axes. Doesn't matter which one. Okay? So the sort of argument that you might have wanted to add in B part, I'm going to write that up now. Okay? So draw these parallel lines here. Right angle, right angle. This would be here. Depending on the longer radius, we get hypotenuse A plus B and leg B minus A or A minus B. And I will say to them, it won't matter. In what follows, as A minus B squared is equal to B minus A squared. And similarly, hypotenuse B plus C and leg B minus C or C minus B. We don't know which. It sort of depends on which one is longer, but we don't really care. Okay, so now I guess then, did I give a name to these? Let's call this X and Y just to be as general as possible. So length xy is going to be the square root of a plus b squared minus a minus b squared. Doesn't matter which one. B minus a if you want it to be. And then b plus c squared minus b minus c squared. So these guys are difference of squares. I should have seen that earlier, actually, but I didn't. And so you'll get a plus b minus a minus b all times a plus b plus a minus b, and then b plus c minus b minus c times b plus c plus b minus c. And so we'll get the square root of the b. The a's will cancel out here, so we'll get 2b times 2a plus the square root of 2b times 2c. Now we can pull out the 4 there, I guess. So xy, square root of 4, and then square root of AB, plus square root of 4, square root of BC, which is just going to be 2. So 2 root AB plus, I didn't give enough space there, 2 root AB plus root BC. I don't know whether or not to factor out the root B like we did before. I'm not entirely convinced. So, knowing that I think it was FGHIJK have lengths 18, 20, 22. We can set up equations without knowing our various radii. So we could just, so one of these is going to have root AB plus root BC is equal to 18. I'm dividing by 2 here. Is equal to 9. We'll also have BC and CA is going to be equal to 10. And then root CA plus root AB is equal to the other one. So 22 divided by 2, which is 11. So I can add all these up, and I'll get 30 is equal to root AB plus root BC plus root CA. I still don't know, is A going to be R3 or is A going to be R2? I have no idea. It doesn't matter. I've given these radii some secret names without worrying about their sizes. Once I solve for A, B, and C, we will just say, oh, the shorter one, that must be R1. That's all we're doing here. Alright, so now I know the sum is... Oh no, there's going to be 2 copies of this. Silly me. Because I'm adding up 2 ABs, 2 CAs, and 2 BCs. So I'll get 2 copies. So then root AB plus root BC plus root CA is 15. And now I can take that and subtract off the individual expressions. So root AB plus root BC is going to be equal to 9. So subtract that off. Root CA is going to be equal to 6. So that means C times A is 36. And I'll say similarly... which one are we missing? We're missing AB for 10, so 15 minus 10 is 5. And BC is the last one, and that should be 4. So squaring, CA is 36, AB is 25, and BC is 16. Now if I multiply them all together, I'll get A squared, B squared, C squared, because I've got 2 A's being multiplied together, 2 C's, and 2 B's, and that'll be 16 times 25 times 36, and that's 4 times 5 times 6, all squared. So ABC is 4 times 5 times 6. And then if I divide that, A will be ABC divided by BC. I know that that's going to be 24 times 5 is 120. So that'll be 120 divided by 16. Divide by 8, and you'll get 15 over 2. B is going to have to be ABC divided by AC, but fortunately I know AC is 36. So 120 divided by 36. That'll be 20 over 6, or 10 over 3. And finally, C is going to be ABC divided by AB. And that'll be 120 divided by 25. So it'll be something over 5, 24 over 5.
So our radii are 15 over 2, which is 7.5, 10 over 3, which is 3.33 repeating, and 24 over 5, which, for the life of me, I can't figure out for right now. Multiplied by 2 on top and bottom will be 48 over 10, so 4.5. Or 4.8. So, I might say, since R1 less than R2 less than R3, we can see R1 is going to be 10 thirds. R2 is 24 fifths. And R3 is 15 halves. And there we go. So, the biggest one turned out to be A, and that was the one that appeared twice in the root 11, which means that this one here is the 22. And the smaller, this one here is the 22. This one here would have to be the 18 and the 20, which is actually what I predicted just based on the pictures. But there we go. We've determined with justification the values of R1, R2, and R3. We didn't really keep R1, R2, and R3 around, although you could have. You could have analyzed each of these 3 different situations. I chose, because I thought it would be a little faster, to instead analyze sort of a general situation. And using this fact that, the negative, a square is the same as if you took the negative number and squared it. So it didn't really matter whether or not the triangle went like this or like this. It doesn't matter which was the middle one, the longest one. Doesn't matter. Does not matter. Alright, so that's question 4, and that finishes off our 2014 paper. If you're looking for more Galois, the next one would be the 2015 Galois paper. So if you want to take a look at that, you're more than welcome to do so, and I either do have videos for that already or should in the future. Okay? Thank you guys so much for watching. If you're looking for more grade 10 level contests, you feel free to check out the Kaylee. It's a multiple choice contest. And I think I'm going to leave it at that. Have a wonderful day. Take care.